Ever grabbed an instant cold pack for, a bump or bruise and just been amazed at how fast it gets cold?
Oh, yeah.
Or watched a fizzy drink and wondered, what's actually making all those bubbles?
Right. It really feels like there's this hidden world of stuff happening all the time in everyday things.
Exactly. And today, we're going to try and peel back some of those layers. Look at that hidden activity.
That's right. We've got this really fascinating collection of chemistry experiments as our source material for this deep dive. Think of it like a guided lab tour.
Okay.
We'll explore things like how electricity can pull substances apart, the energy changes and reactions you can't always see, what tiny living things can do, and even the sort of personalities of different chemicals.
Yeah. So our mission here is basically to take these experiments, these hands-on things, and pull out the main chemical ideas they show.
We're after those aha moments.
Exactly. Those moments where something you've seen maybe 100 times suddenly clicks and makes sense. Think of this as your shortcut to feeling, pretty knowledgeable about some really cool science.
And what's great about these experiments is they often show surprising things about substances we see all the time. We'll be looking closely at the instructions, what was observed, and the questions they raise to kind of bring those insights out for you.
Okay, let's dive right in. Starting with something that sounds a bit like sci-fi.
Yeah.
Using electricity to, separate stuff. Electrolysis.
Yes, electrolysis. And the source has two key experiments on this. The first one is about quantitative electrolysis.
Quantitative. So measuring things.
Exactly. Measuring how much metal you can move from one electrical connection, an electrode, to another using a current over a specific time.
Okay, so the setup, I see it here, involves a copper anode and a copper cathode. Those are the connections.
They sit in a copper sulfate solution, and it's all hooked up to a power supply and an ammeter, which measures the current.
Right. And the experimenters, they weigh these copper pieces really carefully before and after they let the electricity run for about a half an hour?
Yeah, something like that. And they also record the exact current and the time.
So what's the key takeaway there?
Well, what's really insightful is the direct link they find between the amount of copper that dissolves from one electrode, the anode, and the total amount of electricity, the charge that passed through.
Okay.
So by calculating how many copper atoms moved, chemists count these in moles and the total charge in coulombs, you can work out how much electricity it takes to move a specific number of copper atoms.
And is there a known value for that?
There is. The theory predicts it should be around 193,000 coulombs for 1 mole of copper.
Wow, that's specific.
It is. Now, the experiment might not hit that number exactly, and the source material actually prompts you to think about why.
Like experimental errors.
Precisely. Things like, how accurately can you really weigh those electrodes? Are there maybe tiny side reactions happening? It really highlights that even in what seems like a simple setup, getting perfect results is, it's challenging.
Yeah, that makes sense. Real-world science isn't always neat.
Absolutely. But this link between electricity and the amount of substance change, it was fundamental for understanding electrochemistry. Think about electroplating or even how your phone battery works. It's all about controlled movement of ions powered by that electrical charge.
Okay, so that was the quantitative part. What's the second electrolysis experiment?
The second one takes a broader look. It's about what happens when you pass electricity through different solutions, not just copper sulfate. The goal isn't exact measurement this time, but more about identifying what actually forms the electrodes, especially when there's water around.
Right, so the setup is simpler for measuring.
Yeah.
Just the electrodes in a solution, power supply on, and you watch.
You watch carefully. Look for bubbles, maybe solids forming at each electrode. The source gives a table to jot down the solution used and what you see at the positive and negative connections.
And here's the kicker, right? Sometimes things appear that weren't in the original dissolved stuff.
Exactly. That's the key question. Where did those new substances come from? And the big hint is the water.
So the electricity can break down the water itself.
It can, into hydrogen gas and oxygen gas.
Okay. So this experiment pushes you to sort of figure out some general rules. Like, what kinds of things usually appear at the negative electrode, the cathode?
And what usually appears at the positive one, the anode? The source suggests you'll typically find metals or hydrogen at the cathode, and non-metals like oxygen, maybe chlorine, at the anode.
It really shows how electricity can drive chemical change, pulling things apart. Pretty fundamental stuff.
Definitely. Now let's switch gears a bit from electricity to chemical reactions and, crucially, the energy changes that happen with them. And one experiment here sounds particularly cool. It describes this reaction in a flask that changes color back and forth.
Oh, yeah, I saw that. Like a chemical magic trick. You shake a clear liquid, it turns blue, then it just fades back to clear.
Exactly that. And you can repeat it. The ingredients are potassium hydroxide solution, some dextrose that's a sugar, and just a drop of methylene blue indicator.
And shaking it makes it blue.
Shaking it mixes in oxygen from the air. That causes oxidation, and the methylene blue turns blue. Then, as the oxygen gets used up in the solution, a reduction reaction happens, and the indicator turns colorless again. It's a beautiful visual cycle of oxidation and reduction.
Wow. And the source mentions taking the stopper off the flask sometimes. Why is that?
Ah, good point. That's crucial to let more oxygen in.
Okay.
The oxygen is needed for the blue part of the cycle. If you keep it sealed, eventually you'd run out of dissolved oxygen, and the color change would stop. It needs that fresh supply.
So it's like refueling the reaction, a really neat demo of a reversible process.
It really is a dynamic balance. Okay, so from visual changes, let's move to energy changes we can actually feel. Heat.
Like those instant hot and cold packs.
Precisely. They're perfect examples of exothermic and endothermic reactions, which is what the next few experiments explore.
Right. So the source outlines 3 experiments here. First one, dissolving anhydrous copper sulfate in water. It starts as a white powder.
Yes, anhydrous means without water. When you add it to water, it turns into the familiar blue copper sulfate solution. But the key thing they measure is the temperature.
And what happens? Does it get hot or cold?
It gets warmer, the temperature goes up. That tells us it's an exothermic reaction.
Exo, meaning it gives out heat.
Exactly. It releases energy out into the surroundings, into the water.
Okay. Experiment 2, mixing citric acid and sodium hydrogen carbonate with water. This sounds like that baking soda and vinegar reaction. Lots of fizzing.
Very similar. You definitely get fizzing. That's carbon dioxide gas being produced. But crucially, if you measure the temperature here, you'll find it goes down.
Down, so it gets colder.
Yes. This one is endothermic. It absorbs heat from its surroundings to proceed. Endo, meaning in.
I see. So that's the cold pack principle.
You got it. And the third one involves adding zinc powder to copper sulfate solution. We saw copper sulfate earlier.
Yeah, the blue stuff. What happens when you add zinc?
This is a displacement reaction. Zinc is more reactive than copper, so it basically kicks the copper out of the solution. You'd see solid copper forming, maybe a color change, and importantly, the temperature goes up again.
So another exothermic one.
Correct. It also releases heat.
Okay, so based on these results, temperature up for exothermic, down for endothermic. The source then asks you to apply it. Like, which reaction could be in a cold pack? Which in a hot pack or a hand warmer?
Exactly. It connects the lab observation directly to a real-world product. It really makes you think.
Yeah, definitely.
And sticking with energy release, the next experiment compares the heat energy you get from burning different alcohols.
Okay, like different fuels. Methanol, ethanol, propanol, butanol.
Those are the ones. The setup involves burning each alcohol in a little spirit burner, using the flame to heat a measured amount of water in a flask.
And they measure the temperature change of the water, right? And also how much alcohol got used up.
Precisely. You weigh the burner before and after to see how many grams of alcohol burned.
So the goal is to figure out which alcohol gives the most heat, like per gram.
That's the key question. Which one provides the most energy per gram? It's a way to compare their efficiency as fuels, essentially. How much bang for your buck, chemically speaking.
Right, that makes sense. Okay, shifting gears again. Now into biological stuff and materials. Fermentation first. That's beer and winemaking, isn't it?
It is indeed. This experiment looks at the basic process. Yeast breaking down glucose, which is a sugar.
Simple setup too, it seems. Glucose, yeast, warm water in a flask, and a cotton wool plug. Why cotton wool?
The cotton wool lets gas escape, but keeps other things, like airborne microbes, out. Yeast produces gas during fermentation.
And they test that gas, right, by pouring it into lime water.
Yes, lime water is calcium hydroxide solution. If the gas produced is carbon dioxide, which is in fermentation, the lime water will turn cloudy or milky. It's a classic test for CO2.
Okay. And what else comes out of fermentation?
The other main product is ethanol, the alcohol. The source mentions that later on, you'd notice the characteristic smell of alcohol from the flask.
So the basic reaction is glucose turns into...
Glucose, ethanol, plus carbon dioxide. And it's catalyzed, meaning helped along, by enzymes like zymase, which are naturally present in the yeast.
Enzymes. Okay. Staying biological, the next experiment looks at microbes and enzymes in milk. This sounds relevant to food going bad or maybe making cheese.
Both, actually. Microbes and their enzymes are key in food spoilage, but also essential for making things like yogurt and cheese. This experiment looks at different types of milk, UHT, pasteurized, powdered milk, reconstituted with water.
And they just leave them in a warm place for a few days.
That's the first part. Just observe what happens over time. Does it curdle? Smell funny?
And then there's this indicator, this rasarin. What does that do?
Resizurin is pretty neat. It's a dye that changes color depending on how much bacterial activity there is.
How does that work?
Well, if it stays purple, there are hardly any bacteria. Blue means some, pink means more, and if it goes completely colorless, that indicates lots and lots of bacteria.
Ah, so you add it to the milk samples after a few days.
Right, and the color gives you a direct visual clue about the number of bacteria in each type of milk. It shows how processing, like UHT, that ultra-heat treatment, really reduces the initial microbe count compared to pasteurized milk, affecting how quickly it spoils.
Interesting. Okay, let's zoom out from microbes to metals. Transition metals, that's that block in the middle of the periodic table, yeah.
That's the one. Elements like iron, copper, nickel, zinc, they have some really distinct properties. The experiments here look at both their physical nature and their chemical behavior.
Physical, like how hard they are.
Yeah, things like hardness and also malleability. Can you bend them or hammer them flat without them breaking? They also check if they're magnetic.
And how they react with water.
That too. Often, transition metals react very slowly with water, or maybe not at all under normal conditions. The source summarizes their typical physical traits. Usually hard, dense, shiny, good conductors of heat and electricity, malleable and ductile, meaning you can draw them into wires.
Okay. Then they look at their compounds, starting with copper sulfate solution again, but reacting it with ammonia. What happens there?
This is quite characteristic. When you first add a little ammonia to the blue copper sulfate, you usually get a pale blue solid forming a precipitate.
A solid just appears.
Yeah, but then if you keep adding more ammonia, something interesting happens. That solid often dissolves again.
It disappears.
It devolves, yeah, and forms a new solution that's a much deeper, darker blue color.
Why does it do that?
It's forming what's called a complex ion. The copper ion in the center grabs onto several ammonia molecules, forming this larger, intensely colored ion. It's a hallmark of transition metals. Their compounds are very often colored, and they readily form these complex ions.
And they suggest trying this with other transition metal compounds too.
Yes, to show it's a general feature. Nickel compounds might give green or blue complexes. Iron compounds have various colors. It highlights two key properties of their compounds. They're usually colored, and the metals can often exist in different ionic states, leading to compounds with different formulas, like iron 2 oxide and iron 3 oxide.
Fascinating. Okay, nearly there. Next up, halogens. Group 7. Chlorine, bromine, iodine.
That's them. And these experiments look at patterns in how their compounds react. 3 main tests described.
First one, reacting solutions of chloride, bromide, and iodide with silver nitrate. What's the point of that?
This produces silver halide precipitates solids. Silver chloride is white, silver bromide is cream-colored, and silver iodide is yellow. It's a classic way to identify which halide ion is present. These solids are also sensitive to light, especially the silver bromide.
Okay. Second test involves chlorine water, which the source notes is toxic, handle with care, reacting with sodium bromide and sodium iodide solutions.
Right. This shows the reactivity trend within the group. Chlorine is the most reactive halogen here, meaning it can displace or kick out the less reactive halogens from their compounds. So chlorine will react with sodium bromide, producing bromine, which you'd see as maybe an orange-brown color in the solution.
And it does the same with iodide.
Yep. Chlorine reacts with sodium iodide to produce iodine, which might look brown or even purplish depending on the solvent. It clearly shows chlorine is more reactive than bromine, which is more reactive than iodine, ClBrI.
Got it. And the last halogen test uses lead nitrate, also marked toxic, reacting with the potassium halides.
This one looks at forming lead halide precipitates lead chloride, lead bromide, lead iodide, and it mentions exploring how well these dissolve in hot water compared to cold water. Their solubilities are different, which is another property that varies down the group.
So subtle differences even within the same family of elements.
Exactly. Okay, last big experiment. This one sounds like real chemistry detective work, finding the formula of an oxide of copper.
Determining its chemical recipe, basically.
Precisely. Finding the exact ratio of copper atoms to oxygen atoms in copper oxide. The method involves starting with the black powder, copper oxide, and heating it while passing a gas over it, often hydrogen or natural gas, to remove the oxygen,
leaving just the copper behind.
leaving pure brownish pink copper metal behind. It's a reduction reaction.
And the crucial part is measuring the mass changes, right?
Absolutely critical. You need the mass of the empty tube, the mass with the copper oxide before heating, and the mass of the tube and pure copper afterwards.
How do those masses give you the formula?
Well, if you subtract the final mass, 2 plus copper, from the mass before heating, 2 plus copper oxide, that difference is the mass of oxygen that was removed.
Okay.
And if you subtract the empty tube's mass from the final mass, you get the mass of just the copper that's left.
Right, so you have mass of copper and mass of oxygen.
Exactly. Then you use their atomic masses from the periodic table to convert those masses into moles. Remember, moles are just a way of counting large numbers of atoms.
Okay, moles of copper, moles of oxygen.
And then you find the simplest whole number ratio between those two mole amounts. For copper 2 oxide, that ratio comes out as 1 to 1.
Meaning 1 copper atom for every 1 oxygen atom.
You got it, which gives us the chemical formula, CuO. It's a fantastic demonstration of how we use experimental measurements to figure out the fundamental composition of substances.
Wow. We have really covered a lot of ground today. From using electricity to split things, feeling the heat of reactions, seeing fermentation bubble away.
Exploring those colorful transition metals and reactive halogens, right up to calculating a chemical formula from scratch.
It's genuinely amazing how these sort of benchtop experiments can illustrate such big, fundamental chemical ideas.
It really is. And we hope that you listening in have had some of those aha moments we talked about.
Yeah.
You know, seeing that color change back and forth, or understanding why a cold pack gets cold, or why different precipitates form. These visual and tactile clues really help lock in the principles.
It definitely makes you look at the world a bit differently. Thinking about batteries powering things, that's electrolysis like we discussed.
Yeah.
Or cooking, that's heat transfer and chemical changes. Even just breathing involves oxygen reacting in our bodies using enzymes like in the yeast experiment.
Absolutely. It's all connected. And hopefully this deep dive has sparked some curiosity. You know, considering the sheer variety we saw today, it makes you wonder what other everyday things that seem simple on the surface, might actually have some really complex and fascinating chemistry going on underneath, just waiting to be explored.